So this is our second MRI talk. This is a talk that's on encoding and some other miscellaneous topics. So what is this spatial encoding? How do you tell the magnet what part of the body you want to look at? So here's your body. And you can think about imaging occurring in sort of little voxels or little three-dimensional squares. So you can only image each one of these sort of individually. So there's a three-step process. Step one is to select the desired slice. Step two is to encode the spatial information along the row in that slice. And step three is to encode the spatial information along the columns in that particular slice. Localization gradients have identical properties. They're just applied at different times in different directions. Because you have three gradients and three planes, you can localize anything in the body. So let's start out with the slice select gradient. The use of a slice select gradient is used to select the area of interest, just like the other gradients, and this gradient is placed perpendicular to the desired slice plane. The slice selection gradient determines the view, axial, coronal, sagittal, or even some kind of weird oblique view. A selective pulse is placed on top of the gradient, so this RF pulse is applied at the same frequency as the protons in that particular slice plane you want to sample. That way, only the protons in that plane will be affected, and that pulse is called a selective pulse. Now, step two is this phase encoding direction. In other words, encoding spatial information in a vertical direction. In the second step of the process, a gradient is applied, causing the protons in the same row, perpendicular to the gradient, to have the same phase. All the protons at this point will have the same frequency, something like that. So phase encoding takes much longer than frequency encoding, and that's why it's typically done on a thinner portion. For example, in body imaging, by convention, the phase encoding direction is this way, where this dimension here, from here to here, is shorter relative to that. You don't want to spend extra time, let's say, including the I should back up. I should say that it depends on the body part that you're doing. Like, for example, the head is done side to side. This would be the phase encoding direction, because you don't want to lose time including the tip of the nose on phase encoding. So head is side to side, the body is done front to back, and there are a few exceptions, such as breast, which I talked about before, because you have certain artifacts that occur in the phase encoding direction, such as pulsation or respiration. You can see the shadow of the heart right here out in front. Now, you wouldn't want to put that on the breast, so when you're imaging the breast, you would turn it even though it will cost you extra time. That way, if you do have some artifacts, they occur in this direction, which is a little bit more, it's actually much less likely to occur. You're much more likely to get breathing and heart beating on artifact and this kind of stuff that way, and that's why you would do the phase encoding direction in this plane, even though it would take you a little bit longer. So, I mentioned that phase encoding is a problem with regard to time, and it's actually quite a bit of a problem, because the formula for determining the duration of the study is your TR, which you remember is the time, the time between each pulse that's given, the number of phase encoding steps, and then the number of excitations. So the third step is this frequency encoding direction, and this is just a gradient placed in the opposite direction perpendicular to the phase encoding direction. So if you're doing phase encoding up from front to back, frequency encoding will be from side to side. Now this one's faster relative to the phase encoding direction. And after it's applied, each one of the protons will have identical frequencies. Okay, so let's take a look at how this works, and we're going to do it in one of these schematics. It's important to be able to interpret one of these things and be familiar with it, so we're going to work through. So the first thing that's done is a slice selection, right? The slice selection gradient is applied, and it's applied at the same time as the 90-degree RF pulse called the selective pulse. So there's our 90-degree pulse, there's our slice selection gradient. Now the next thing that's done is the phase encoding and the frequency encoding gradients. So those are applied next. Next we give a 180-degree refocusing pulse. And before and after this 180-degree pulse, two identical slice selection gradient lobes are applied, and the reason this is done is to correct undesirable spin on the edge of the slice. So something like that. And then lastly, a second frequency encoding gradient is applied at the same time as you do a readout echo. So there. And then you repeat this as many times as phase encoding steps that you've got. And that is a spin echo sequence. And just as a refresher, this time period here would be the TR, and this time period here would be the TE. So what about slice thickness? How do you tell the magnet to make a thin slice or a thick slice? How do you do that? Slice thickness is manipulated by adjusting both the bandwidth of the selective pulse and the amplitude of the slice selection gradient. So slice thickness is governed by the following equation. Thickness is the transmit RF over the slice selection gradient times some constant. The bigger the RF, the thicker the slice. So something like that. See, thicker, that's going to give you, or a bigger RF is going to give you a thicker slice. Now, less is more. In other words, or point being that using a narrow RF pulse bandwidth will take longer to excite, resulting in a longer scan time. So thinner slices equals longer study, which, you could probably have guessed that. Now, with regard to that gradient, less of a gradient is going to equal a thicker slice, and like here, you can always say, well, these are different than those. More of a gradient is going to allow for multiple slices where each little color change is going to equal a different slice. So that's the opposite of the RF, whereas thick RF equals thicker slice, thick or less of a gradient is going to equal a thicker slice. So it's the opposite. Okay, now let's talk about spatial resolution. So remember, spatial resolution is your ability to tell that two things that are sitting next to each other are separate and not one thing. In X-ray and in MAMO, we talked about line pairs per millimeter, those kinds of things. So spatial resolution is governed by the size of the voxel. And the voxel size is determined by the matrix field of view and slice thickness. So if you've got more voxels here, in this case we have 4, versus one voxel, The guy that has 4 voxels, which each one showing an individual thing, you're going to be able to tell that there's 2 different things. But in the big voxel, 1 voxel, that signal's just going to get averaged together, and it's just going to look like there's 1. So more voxels, better spatial resolution. So like I mentioned before, voxel size is determined by your slice thickness, your field of view, and your matrix size. And the point of this equation is, for better spatial resolution, you want less field of view and more matrix. And the way that I remember that is, think about your field of view if you were looking into a microscope, right? Relative to using your naked eye. Now, your field of view is going to decrease a lot because, with your naked eye, you can see like the entire wall or the entire table or whatever. You look down in the microscope and you can only see a small amount, but your spatial resolution's way better, right? So that's the way that I remember that. Matrix is like, the movie The Matrix. You can see things better once you have a better grasp of the matrix, right? So that's how I keep that straight. Or you can just remember that they're opposite. All right. Now, remember that we said slice thickness, right, is also a player in voxel size. So going back into what makes thin slices and thick slices, remember that less gradient is going to equal a thicker slice, right? And a larger transmit RF pulse is going to equal a thicker slice. So here's a summary. More matrix, less field of view, thinner slices with a smaller readout or a bigger slice select gradient is going to improve your spatial resolution. Now let's talk about signal-to-noise ratio. So factors in affecting signal-to-noise ratio. So first you have to sort of understand what noise is. Noise is just a random variation in signal that leads to degradation in the signal itself. And in MRI, the primary source of this noise is the patient's body. So overall, the larger your voxel, this is the opposite of spatial resolution, the larger the voxel, the better the signal to noise. And the way that I think about that is if you think about the background noise sort of being a constant, the more signal you can bring in, the better you can improve your signal to noise ratio. So like if you have a bigger sampling volume, in other words, a bigger voxel, you're going to have more signal. If you have a larger field strength, remember from back to the very first lecture where I was showing that at the 3 Tesla, it was turning more of the things over relative to a 0.5 Tesla. So more field strength, bigger voxel size, the opposite of signal to noise ratio. So small voxels taking in a little bit of signal each versus a big voxel taking in a lot of signal. So let's do a compare and contrast here. So remember, for spatial resolution, to improve that, we wanted what? Big matrix, small field of view, and thin slices, which required a small readout and a bigger slice select gradient. Signal to noise wants a small voxel, right? So we want small matrix, large field of view, and thicker slices, which is going to be the opposite, thicker readout and a smaller slice select gradient. And then, of course, a stronger magnet as well. So, stronger magnet, field strength. Another thing that improves your signal to noise also is a smaller surface coil. That's why it's important to use the right coil. That's why breast coils have a breast coil, or a wrist. You wouldn't want to use the body coil on a wrist, those kinds of things. That improves your signal to noise ratio. If you've ever seen the MR tech put the wrong coil on, the images don't look as good. The other thing is a number of excitations. More excitations you perform, the more signal you get. The main trade-off to this, if you remember back to the table time thing, is that number of excitations is one of the factors that's going to play into how long you're on the table, like TR, right? TR, your phase encoding steps and your excitations are going to affect your table time. A narrow receiver bandwidth. So a fat receiver bandwidth gives you rapid sampling of data. A narrow bandwidth gives you slow sampling of data. Since noise is constant, the fatter band will pick up more noise. So fat bandwidth equals decreased signal to noise. A narrow bandwidth equals increased signal to noise. All right, here's our summary chart. We're going to put it all together here. So thicker slices, what will that do? That's going to improve our signal to noise, right? Bigger sampling. It's going to make our, because remember this is all about voxel size for signal to noise, spatial resolution. You want smaller voxels. Signal to noise, you want bigger voxels. So you want the opposite. And that's not in our equation for table time. Remember, our table time equation is excitations, TE, and or TR, and phase encoding. So, and then large field of view is going to, so remember, signal to noise ratio is basically the opposite of spatial resolution because of the voxel size. So remember, you want to look in the microscope, and that has nothing to do with table time. Okay, so for a matrix, a larger matrix, remember that signal to noise and spatial resolution are all about bigger voxels and smaller voxels. So a larger matrix is going to decrease your signal to noise and increase your spatial resolution. Now this can, now when I say larger matrix, what I actually mean is a finer matrix, a matrix that's consisting of more pixels. It's important also to point out that spatial resolution is determined by matrix size in the frequency encoding direction, while scan time is determined by matrix in the phase encoding direction. So more matrix, more phase encoding, and that can result in a longer table time. Now remember, we said that greater field strength increases your signal with your noise staying constant, so that improves your signal to noise ratio. Should have no effect on spatial resolution. The effect on table time is probably marginal. You may be able to argue that by increasing field strength, this increases tissue T1 times and therefore acquisition time. I would say it's marginal. Probably, I would say that it doesn't affect table time in any way that actually matters. Now, remember that receiver bandwidth, a fat bandwidth, gives you rapid sampling of data, and a narrow bandwidth gives you slow sampling of data. And since noise is constant, the fatter band will pick up more noise. So a fatter receiver bandwidth equals a decrease in signal to noise ratio. Now, receiver bandwidth does not have an effect on spatial resolution. And if you've got a larger bandwidth, then you this also will decrease your table time. Now, more excitations per slice, that's going to result in more signal, so improved signal to noise ratio. That should not have any effect on spatial resolution because it's not affecting the voxel size. And as I pointed out earlier, that number of excitations is part of that table time formula, so that will make your table time go up as well. All right, that's the end of this talk. The next one is we're going to go through all the different pulse sequences.